going to start. Hello, welcome to my talk. My name is Bartosz Golaszewski. I'm originally from Poland, but I've been living in France for the past 6 years. And this is my first time at your conference, and first time in Russia in general, so I'm very happy to be here. I work for Libre. We are a small consultancy based in southern France. We are around 30 engineers at the office and a couple of guys worldwide remotely. We specialize in embedded systems based on the Linux kernel. We do all kinds of work in this field, so we do upstream kernel development and maintenance. We help our clients launch consumer electronic products from hardware design through software engineering to maintenance. We are the founding members of the kernel CI.org project, so the continuous integration for the Linux kernel, and we have worked on projects such as Project Aura, for instance, so the modular phone from Google. And me personally, I've been in this field for 9 years now. Over this time, I've been contributing to many open source projects, including the Linux kernel and many Userspace components. I created and maintain libgpiod, about which this talk is going to be later on. And as of this release, as of this kernel release, I also co-maintain the GPIO subsystem in the kernel. So before I start, how many of you work on embedded Linux in general, like on a daily basis? So some of you. And how many of you have used GPIOs and have a notion of what they are? Okay, so some of you as well. So yeah, I was told that my presentation needs some funny pictures. I couldn't make up any funny pictures that would have anything to do with the presentation, so these are just random two alpine marmots fighting over a carrot. This has nothing to do with the presentation, but at least there's a funny picture. And the agenda for today is going to be as follows. So I'm going to give you a short introduction into GPIOs in general, then a brief overview of the GPIO subsystem and the kernel. Then we're going to talk about the two user APIs exported by the Linux kernel to the Userspace, so the old deprecated sysfs interface and the new character device that you should be using from now on. Later we're going to talk about libgpiod. So this is the project that is the Userspace counterpart, Userspace part of the new character device that makes it easier to use. We're going to go through what it is, examples of usage, language bindings, and the future plans. So GPIO stands for General Purpose Input Output, and it's a relatively simple idea. It's a pin that you can program. It always has two values, so it's either high or low. And it can be configured in two modes. So either it's in something that we refer to as input mode, where someone else is driving the line and we read this value, or it can be configured in output mode, when we are the ones driving the line for someone else to read. And in input mode, GPIOs can also serve as sources of interrupt, so we can get notified about a change in state. By the way, if there are any questions at any point, please stop me, raise your hand, and let's have a discussion. And GPIOs are provided by either SoCs themselves, so SoCs have pins and they can be configured to be GPIOs, some of them of course, or if there are not enough, you need more, you can use external integrated circuits, which we refer to as expanders, GPIO expanders, which are connected to the SoC via a simple bus like I2C or SPI. The applications. So we, despite the relative triviality of the subsystem, they're used all around the place, everywhere where you need this simple logic of high or low. So you can have buttons that when you press them, they raise the line. You're notified about button press. You can drive LEDs. This is a common application. You drive LEDs with GPIOs. Robotics, where you drive simple motors, sensors like level sensors, where you only need to know that some level has been reached. You can use GPIOs. Yeah, this kind of applications. And this is basically how the software stack looks, both in the kernel and the user space. So at the very bottom, you have the hardware. As I said, this is the SoC or an expander. The GPIO chip driver talks directly to the chip, to the GPIO chip controller over either by poking registers if it's register mapped, or sending I2C messages, and then implements a certain interface that is defined by the GPIO lib kernel framework. So it implements all the functions that the GPIO lib framework expects, which in turn allows the GPIO lib component to export an API for in-kernel users and for the Userspace users, which is uniform, so that we can use all kinds of GPIO chips by issuing the same kind of by the same set of operations. And in Userspace, we currently have two user APIs that I'm going to be talking about, so the sysfs and the GPIO character device. In the kernel, we also actually have two coexisting frameworks. One is the old legacy framework, which is, it relies basically on numbers. So you have a global number space with every GPIO assigned a global number, and you have to actually use it in this way that you request a GPIO by number and then you refer to it by number. In this case, we're setting its direction to output and setting its default value to 1. This is now deprecated because this is an old framework and it doesn't give you fine-grained control enough for today's standards. This is why we have a second, a newer framework for GPIOs in the kernel, where we use opaque structures called GPIO descriptors. And we actually associate GPIO resources, in this case lines, with consumers. So when you try to get a line, you actually pass to this new function GPIO get, you pass the device structure because we actually associate the resources with consumers. This looks a bit like this. So we have a GPIO chip, and it exports a set of lines. In this case, we have 8 lines, and then we have the consumers on the right. So we have a an EEPROM driver, or a regulator, or a reset controller, and in device tree, or in board files in legacy, or in ACPI, we assign lines to consumers, and we tell it, okay, so this line is going to be the write protect, is going to be controlling the line protect pin of the EEPROM driver. So now the EEPROM driver will know that in order to write, it has to, for instance, raise the line high before executing any write operations on the EEPROM driver. Or we can disable and enable a regulator that is a fixed regulator, for instance, that is being driven by GPIOs. And yeah, we have a new set of functions that give you more fine-grained control over the GPIO. So we have, for instance, this example shows you that you can use in a sleeping context, in a context that can sleep. You can use a function that tells explicitly, okay, this we are setting the GPIO value, but in this case we can sleep. Okay, so is that clear? This is a very brief overview. So in general, the idea is that you should be writing drivers for devices that make use of GPIOs, but this is not always possible, or not always necessary, or sometimes it's simply unwanted. For instance, oftentimes when you use power switches or relays and they are controlled by GPIOs, you want to control them from Userspace. Sometimes it's, so now it's, I see Johan in the room, so he's taking care of that, but up until recently, the GPS devices existed solely in Userspace. So you would talk to a GPS over a serial port, over virtually a serial console, and then if you wanted to disable the device, you can wire the regulator to a GPIO and simply toggle it from Userspace and disable it. And certain users, it's my experience that certain users actually prefer to use GPIOs from Userspace. It's mostly in intelligent home systems where you have some Userspace applications that talk to various components, and they want to actually toggle GPIOs from Userspace, and robotics as well. So who has already used this sysfs subsystem, so sys class GPIO? So this is wrong. Like, don't do it. This subsystem is very bad. It's been actually merged into the Linux kernel during the time where there was no active maintenance of the GPIO subsystem, so it just slipped by and got merged, and now we have to live with it. So the problems are several. First, this is a global state that exists in sysfs, so it's not tied to any process. So let's imagine that you have a process that does something to GPIOs, exports something, sets some values, and then dies, crashes. You never get back to default. This is going to stay like this. Because sysfs is actually, so this framework, yeah, this is interesting. So this framework is actually the user of the old legacy number space based kernel, kernel API. So if you look into the code, it actually does that. It exports the GPIOs using the old functions. Next thing is that we can have processes concurrently accessing the GPIOs and getting in each other's way. And then the API is quite cumbersome. It's difficult to use because you have to deal with several files for each GPIO line. It's difficult to look up lines by name. It's difficult to poll them, and not reliable as well, which I'm going to talk about in a moment. And also the whole concept is wrong because we basically try to represent something that is a two-level hierarchy with a flat representation. So yeah, this is something that we don't really want. Just to show you a quick demo of how it works for those of you who don't have any experience with it. Basically, in sys we have, can you see this? Is it okay? In sys class GPIO, we have a set of files. So by default, it's only export and export. By the way, I'm going to be using here and later on in my presentation a kernel module that is called GPIO-mockup. This is a testing module which creates a set of virtual GPIO chips. This is nice for testing, so you can check it out. So now I'm going to load the GPIO mockup module, and we now have a set of GPIO chip directories in sys class GPIO. If you go into one of those directories, you're going to see a couple of files. The ones that interest us the most are the label, so you know how the chip is called, and then the base number of the GPIOs. So for this chip, the offsets of GPIO line, like the numbers of GPIO lines start at 484, and we have 4 of them. And now, if you want to export a line, you just simply write the number of the lines you wish to export into the export file. Now you have a new directory. It's called GPIO 484. You go inside and you have another couple of files. You have the value file, which is the most interesting probably. Now the value is 0, and we see that the direction is output, so we're actually driving the line. So if we write 1 to value, we change its value, and now we're driving it high. And this is how it works. Once you're done, you write the same number to the unexport file, and this is it. I don't want to get into much detail about it because this is not really something you should be using. So yeah, to address all the problems that we have with this subsystem, we have created a new interface, and this has been merged in kernel 4.8. So now, for each device, for each GPIO chip registered in the system, we're going to create a new device in /dev. So it's going to be GPIO chip 1, GPIO chip 0, GPIO 1, and so forth. And since this is a regular character device, you work with it just as you would with any other character device. So you can open it, you can call ioctl on it, you can poll it for events. I'm going to show it soon, and then you can read the events from it, and you can close it. And since this is a character device, and it's associated for a process, from a process's point of view, this is associated with a file descriptor. Once the process dies, the device is being closed, and everything returns back to default if you have changed something. Also, we now can request multiple lines at once with a single IO control. We can set values and read values of multiple lines at once with a single context switch. We can easily look up names, look up GPIO lines by names, or chips by their names and labels. We can now give hints to the kernel or specify to the kernel how to drive certain lines. So you have the open source and open drain flags. This is basically the way to tell the kernel how to drive the lines. You have now the consumer and user strings. So when you export a line, up until this point, you wouldn't be able to tell who's, like, let's say you try to export a line, but it's busy. Like the kernel is telling you, okay, I'm not letting you do it because it's being used. Now you can actually look up who's using the line. So it's going to tell you if it's some kernel thread or is it some user space process, and if yes, which process it is. We now have UE events, like we of course had UE events all along, but in this case we have another UE event now which will tell you the path to the device that is being created. And we now have reliable polling, and this is interesting. So in sysfs, like just to give you an idea how badly designed this subsystem is, if you want to be notified about interrupts from Userspace in sysfs, you'd have to poll the value file, like the file descriptor associated with this file. And then when the poll returns a positive value, so you're being told that that there is an event on this file, you actually either have to close and reopen it and then reread it, or else seek to the beginning and then reread it. But these events are not buffered, so you're being told there was an event, but if you don't manage to read it fast enough, it's going to be you're going to miss it. So in case of the character device, it's actually buffered. Let's say your poll returns, and you can read event, and they're going to arrive in the exact order that they've been generated. So this is reliable if you need actually if you must not miss any events. So the user API lives in Linux/GPIO.h. And this is the file that defines all the data structures and IO control numbers that deal with the GPIO character device. It's logically split into parts, so you have the part to get chip information, line information, then for getting, reading, and setting line values, for requesting lines, of course, for a separate section for requesting lines for events, for interrupts, polling for those events, and reading them. So you have basically one or two data structures for each of these operations and a number of IO controls. And so now the problem with this API is, of course, that the previous interface allowed you to script things a lot. So you could just write your shell scripts or just toggle GPIOs from Userspace, and with a character device and with a set of system calls that you need to use to interact with it, you no longer have this possibility. So we created libgpiod. So this is the project that will allow you to actually convert all your scripts and use the character device easily, much easier than the original kernel interface. So a bit of history behind this project. We at Libre have designed this power measurement cape. It's called ACME, and it comes together with power measurement probes. And on these probes, outside from the power monitor, we have a power switch, and we wanted to drive it. For instance, if you're measuring a board, you want to power cycle it to just measure its power consumption on boot, at boot time. And yeah, so these monitors were actually driven by industrial input-output drivers, but we also wanted to toggle the power switches. For that, I started out by trying to add those power switches to the IIO driver that was driving the power monitors, but I was told, and rightfully so, that this has nothing to do with the monitor itself. This is just a random GPIO, so it's not the place for it. Then I tried, I found out that it was probably the 15th person that was trying to add regulators controlled from Userspace. I was told by Mark Brown that, yeah, not the first one, but this is simply wrong, and we never do it. And eventually I figured out that the right approach would be to use the character device. But yeah, I noticed how hard it is to use it. So I decided to write a Userspace, a set of Userspace tools and a library for that. I started out during the Christmas break 2016, and a month later I released the first version. This was very simple and contained just the library, and then another 2 versions were released in the unstable series until a year later the v1.0 was released. It contained most of the features that you can find there today, and the current stable version is 1.1.1. 1.2 is coming soon. I think I'm going to release it soon because I have enough changes already, and it might be released this weekend. And yeah, I still support O.3 series, since this series has been packaged in many distributions and people started using it, so I decided that since the 1.0 version of the library is not backwards compatible, I decided to still support the O.3 series with bug fixes. What's inside? So we have the C API, which is much easier to use than the I/O controls from the kernel. We have a set of command line tools. So this is interesting because this will allow you to replace all your scripts that deal with sysfs. We have a custom test suite. So again, we're working with the GPIO mockup module to test both the kernel UAPI and the library. And we have, and we work with the interrupt simulator, and we have language bindings to C++ and Python. Again, the API is split logically just as the kernel API, except that outside from regular chip and line operations, we have two other things that stand out, which is the simple API, to which just referred to in code as contextless API, which allows you to call functions without dealing with resource allocation and freeing. And then we have iterators, which allow you to iterate over GPIO chips in the system and over lines exposed by those chips. So this is just a quick example of how you use the C API. So you open the line, then you get the line at offset 3, then you request it for input, you tell the library what consumer it is, what consumer you are, then you read the line value, and you close the chip. So it's 5 functions, in this case, which you use for setting a value of a single line. It's getting more complicated when you have multiple lines. And this is just a quick example of how you poll for events. So you open the chip again, get the line, set it for, request the line for rising edge events. So we're going to only look for, only monitor the rising edge events. Then you poll it. You can actually get the descriptor and use your own polling function, but in this case it's a helper that waits for an event on a single line. Then you read the event, which fills out this structure, GPIO line event, and you can print the event type and its timestamp when it occurred, and then you close the chip. So what's more interesting for most people are the command line tools. So this is something, just let me load the module with named lines. Oh yeah, this is gonna help us. Okay, so we have 6 tools. They are kind of inspired by the I2C tools, so names might sound similarly. So the first one is the easiest. It's called GPIO detect. This just tells you what chips are there in the system and how many lines they export. The first column is the GPIO chip name, then there's its label and the number of lines. And the second tool is GPIO info. This actually tells you how many lines, of course, again, tells you how many lines there are in each chip, and also it gives you some information about the line. So for each line, it's offset, its name. If it's named, it can be unnamed. In this case, the testing driver is, for the testing driver, we're using the names. Then if it's used, then it's input or output mode, and then active high. Active high and active low, it's a way to describe a line. So when a line is referred to as active low, it means that it's a value. When it's high, we interpret high line as 1, and if it's active low, we interpret a low-driven line as 1. The next tools are GPIO get and GPIO set. So the names are obvious. You use GPIO. I'm just gonna make it a bit smaller. Yeah. You use GPIO get to read GPIO chip 0 to read a set of lines. So we pass it the name of the chip, and in this case we're giving it a list of line offsets, and it gives us a list of values of these lines in the exact order. So now if we let's set one of these lines. So let's do 1 equals 1. Let's set the value of invalid offset y. Now, so we set its value to 1, and now you can see the line at offset 1 is set high. So this is a bit misleading, because in this case, like these lines exported by GPIO mockup are floating pins. So once you set them, they stay at it, but they keep the value. But it can be different if you have a resistor, for example, behind an actual hardware line. It can be driven low or high by default, in which case once the GPIO set program exits, they're going to return to default. So in this case, you may want to specify a mode for GPIO set. So you set -- mode equals wait, for instance. In this case, GPIO set will not exit until you press enter. So there's that, and then the next little tool is called GPIO find. It just gives you, for a given name of a line, in this case GPIO mockup B3, it gives you the name of the chip corresponding to it and its offset of this line on this chip. And the last tool is GPIO mon, which actually allows you to monitor events from Userspace. In this case, we're going to monitor the line 0 at GPIO chip 0, and we're going to use a feature of GPIO mockup driver, which exports a set of files in debug.fs, which allow you to simulate interrupts using the in-kernel interrupt simulator. So when I write 1 to offset 0, we're getting an event, a rising edge event. If you write 0, you're getting a falling edge event, and this is human readable, but you can actually specify a format. If you specify the format -- format option, and there are several modifiers available. They're well documented. You can specify a format that is easily parsable by scripts. So in this case, we're going to get again the offset of the line, the type of event, the seconds, and the nanoseconds of the timestamp, respectively. So these are the tools that we support. Next, we have the language bindings. So for now, there are C++ and Python bindings. In C++, we use a relatively modern standard, C++ 11. We simply didn't need any other features. This makes the code much easier to use. This makes the API much easier to use. So we wrap all the C classes in C++. You get all the perks of C++, so reference counting when dealing with resources, exception safe code. The tools are re-implemented in C++ as an example. We also include many other examples, and the API is again fully documented in Doxygen. Just to give you an idea how it works, so we open the chip in the constructor, we get the lines. In this case, we get a set of lines, which is much easier in C++ than in C, where we would have to fill out arrays and all that. We request the lines for output, and we give them the default values, and then we simply set the values. This is how it works. You can catch exceptions and don't need to check errors after every call. And this is just an example of how to monitor lines for events from C++. Again, get lines, request them for both edges, and then wait a number of nanoseconds, read the event, and you can print it. This is how it works. Python 3. So this was something that was requested by many users, and since version 1.1, sorry, we finally have it. So this is written as a Python extension, native extension in C. Again, the entire API is wrapped in Python C classes. It's documented in PyDoc. You can use help from Python itself. Again, we re-implement the tools, we include examples, and actually I learned that Adafruit Blinka software suite uses Python from libgpiod for using GPIOs, for toggling GPIOs. Just another example of how we use Python. It looks very similar to C, just we have the with statement, because Python doesn't guarantee us freeing the resources. And yeah, so coming soon is debug bindings. This is something like we actually need to toggle GPIOs. We would want to toggle GPIOs over the network, and I figured that maybe using like calling dbus methods over the network would be a nice way to do it. This is work in progress. There is some preliminary code already available on my GitHub. It's going to be a daemon written in C based on gdbus and gudev libraries. We're going to export chips and lines as objects, and then we're going to export their properties like name, label, and so forth, and certain methods. So we're going to be able to request the lines, set values, get values, etc. Signal, like the GPIO line interrupts are going to work as dbus signals, and yeah, we're probably going to use it for Baby Brachme. as a way to complement the libgpiO network capabilities. And future. So after dbus bindings, it's probably going to be feature complete. I'm not going to add many new features for that. We're going to add proper testing for Python and C++, and we're also going to support new Userspace features of the kernel API, because there are some that are brewing currently on the mailing list. Yeah, another feature that I want to implement is running external processes on GPIO Mon when there are events occurring, and where to get it. So this is hosted at kernel.org. You can find the source at my Git in my Git tree on git.kernel.org. The releases are available there as well as tarballs. The project has been packaged in Meta Open Embedded and built by me, and I actually maintain these recipes. And some other people have packaged it for Fedora, Arch, Debian, I think some other distributions as well. Contributions and bug reports are welcome. Please send emails to Linux GPIO, to the Linux GPIO kernel mailing list. Just prefix it with libgpiod. And that's it. So just for your information, you're going to be able to download the slides. At the end of the slides, I included some examples of the kernel user API, so all the IO controls and all that. I didn't want to bore you with that, because this is largely irrelevant now with libgpiod, so you don't really want to use them. And yeah, so I think we're good. And are there any questions? Yeah, there are 2 questions here.
Okay, just a moment. Please. I saw this person first.
Hello, my name is Dan, but sorry, my English bad. I have asked what a problem you have when integrate this library into C++ 11.
What problems did I have with C? None at all, actually. It was relatively easy.
And the second, is have to ask, plan you integrate in C++ 14 and 17?
Yeah, good question. I will not. If you look in the code, it's relatively easy. So the things that I needed from modern C++ were already included all in C++ 11, and I decided that I will use the oldest standard that I can get away with while still writing reasonably modern code. Mm-hmm. So I don't plan on integrating. Oh yeah, definitely, yeah, of course.
And last ask is, plan you integrate this library with Qt library several, maybe in a style of Q serial port or another?
So I would have to rely on external contributions for that, because I'm definitely not a developer of graphical interfaces in any way. So I actually contributed a bit to Qt, but it was also only for some low-level things in Pulse Audio. So I don't deal with graphical interfaces. So I don't plan on doing it myself. But if someone did it, I would be happy to integrate it.
Okay. My opinion, it's Qt. It's a cool library, and if this library integrate in Qt, maybe some profit. My opinion. Sorry.
Thanks for your opinion. The next question, please.
Thank you for my presentation. Excuse me for my awful English. Question is. We need in GPIO lib, we need to know what GPIO chip is represent GPIO line that we need use in Userspace.
I'm sorry, I didn't get it. Could you repeat?
GPIO chip. Yeah. When we write some application code in Userspace that consumes some GPIO line, we need to know what name of GPIO chip or number of GPIO chip that represents some GPIO line that we need.
So the easiest approach would be to define a name for it. Like, are you using device tree or? If you're using device tree, you can define names for GPIO lines in device tree. And they will appear in Userspace, just as I was showing. This was not on a slide. This was in my example. I was showing you the GPIO info command. There was a column with lines. So if you call your line something in GPIO in device tree, it will appear in this column in GPIO info, and you're going to know the offset and the chip on which this line exists. So you can actually use the GPIO find tool or GPIOD line find function in CAPI to find a line by name. So you say
only by name.
Yeah. You can refer to lines by its chip and offset or by its name.
Oh, thank you.
So I have a next question. Thank you for your talk. So I have actually two questions. The first one is related to the concurrent usage of GPIO lines. So in some cases I would like to have one process to write the lines and some process to just read them. So is it possible with this new interface to have some multi-process ownership, like ownership for line?
It's a very good question. No, it's not possible. So you can actually, multiple processes can read information about a line at the same time, but they cannot read values or set values. In fact, they cannot request a line, so like reserve a line at the same time. So once one process does it, another process will not be able to do it, neither will the kernel. So if the kernel allows the process to take it first, then even if a driver tries to acquire the same GPIO, it will not be able to. But I understand the need for that. This is why I'm writing the dbus daemon, which will allow it.
And second question is related to it comes from your demo about the reading several lines at the same point. So the question is, in some cases, I need to get the low latency between reading the lines and attach to the one particular time. So is it possible to measure time of reading the lines in the kernel and return the values to the user space with the time mark?
You can get the timestamps for interrupts, but not for reading or writing of lines. Unless you
I didn't get you actually, so probably I'll ask again. So I'm controlling the several lines. So and I'd like to have values of these lines.
You said failures?
Simultaneously.
Okay.
So like I have the timestamp for these values, because if I get values from the kernel space, I measure timestamp in the user space, and this would be the latency between these two events.
So you want, if I get you right, you want to read lines, read or write? Read lines, right? Read lines, and you need the latency between
reading lines. I would like to attach all these values to one timestamp. So how to do this?
It actually, like, I don't know if this answers your question, but if the GPIO driver implements the get multiple callback in kernel.
Yeah, I understand. But I'm asking about your user space tools.
It will use this callback eventually, because it will do one context switch to set all the lines, and eventually in the GPIO lib in kernel, it will end up using the get multiple callback of the driver.
But will I get the timestamp of this reading on the user space?
You will not get a timestamp of a reading. It's not. It's not implemented. There's no such way. You cannot get an actual timestamp of a read.
Yeah. Okay. Got it. Thanks.
This isn't implemented.
Yeah. Sorry. Bartosz, you mentioned new feature of resetting device to default state. Just to confirm, when is happening?
I'm sorry. I didn't. I'm sorry, I didn't get.
Just to
confirm in which cases it's happening. As I understand, you need call close procedure which will persist your changes.
So the close frees the memory associated, like with this process, for allocated for all the data structures for GPIO chip, and also for and also closes the file descriptor. But if your process dies, then the file descriptor will be closed automatically in the kernel, and all the structures in the kernel will be freed automatically, and the state of this GPIO chip will return to default.
So in which conditions we will revert to default?
When the file descriptor associated with GPIO chip is closed. This is the condition.
So we have to save our state before.
What do you mean by saving your state?
I mean how to persist our changes.
You cannot, like, unless the pin is a floating pin, you cannot really keep your changes when your process exits.
So, for example, to keep GPS device powered up, I need constantly running process.
Yeah, but you usually have some daemon running, and you can simply have your GPIOs exported and kept alive, kept high, driven high or driven low. This was the whole idea behind the new framework, so that the state is tied to a process. So when the process is gone, the state is reverted to default.
Okay, thank you.
Thank you for your questions. I would notice that we have already gone out of the time slot, so
yeah,
we need our speaker to decide whom should we hand a T-shirt for the best question.
So let's go for the Mr. in the first row.
Mr. in the first row. Oh, Kirill. Yeah. Which size is yours?
Thank you.
What's your opinion about coffee?
You can catch me outside if you have any more questions. I'll be glad to answer it. Thank you.